Okay, I think it's recording again. So we're talking about bromination versus chlorination. Bromination has an endothermic rate determining step, and chlorination has an exothermic rate determining step. And that is actually the key. The more endothermic the rate determining step, the more selectivity you can introduce hydrogens. So we're going to get two possible products, right, from either bromination or chlorination. We can either get 1 bromopropane or 2 bromopropane. For chlorination, we can get either 1 chloropropane or 2 chloropropane. And the rate determining step, we know that the rate determining step is step 1. Hydrogen, so the major product will be the secondary to form HBr and the carbon radical. And we know that the secondary hydrogen costs 98.5 kilocalories per mole to break. And we know that the HBr bond releases 87 kilocalories per mole. I'm pretty sure that number is right. If it's 86, don't shoot me. Right? So we can calculate delta H of reaction here. Right? We've put in 98.5 kilocalories per mole. We're only getting back 87. The situation is even worse for the primary hydrogen, right? Because that primary CH bond is 101 kilocalories per mole. So we have to put in 101 kilocalories per mole, but we still only get back 87 kilocalories per mole when we form the HBr and the primary radical. So delta H of reaction for that one, right, is plus 14 kilocalories per mole. The difference between those two, 2.5 kilocalories per mole in the bond dissociation energy, DH naught. So the products, the primary versus the secondary radical, are 2.5 kilocalories per mole apart. If we draw our energy diagram and we put those reactions side by side, here's our starting material. The primary product is 14 kilocalories per mole higher. The secondary product is 11.5 kilocalories per mole. So we're going to do this. We know that the difference here is 2.5 kilocalories per mole. And we know that this gap from the starting material to the secondary, right, that goes up by 11.5. So if we add that 11.5 to this 2.5 kilocalories per mole difference, that primary radical is 14.5 kilocalories per mole higher. In terms of relative reactivity, what we're really interested in is the difference in the transition state energies, right? Which is the difference in activation energy. How much more activation energy does it take to go over this hump to get to the primary radical than the secondary radical? So that's where we can use the Arrhenius equation.
To A e to the negative e a over RT.
Right, so this is the rate constant, it's lowercase k. A is the pre-exponential factor. If you know about collision theory, hopefully you covered collision theory in Gen Chem, you know that the rate constant depends on, right, the rate of reaction depends on Z, which is the number of collisions, times P, which is the proportion with the correct orientation to react, times F, which is the fraction, and F is equal to e to the minus EA over RT. The proportion with the correct orientation and the number of collisions get lumped together into the pre-exponential factor, right? For a radical, the proportion with the correct orientation is 100% because it's a single atom colliding, so it's not like there's an orientation factor where it has to approach from a certain angle in order to react, right? And the number of collisions is dependent on the number of that type of hydrogen. So we've kind of corrected when we calculate our relative reactivity for this factor by dividing through by this statistical factor. So it's really in terms of a catalyzed reaction versus an uncatalyzed reaction, right? So if we have an uncatalyzed reaction that looks like that, there's a certain activation energy, right? The activation energy for the uncat. And then if you have a reaction that's catalyzed, typically it's going through some kind of intermediate, which means it's going over two different energy humps, right? And so now we've got a different activation energy for the catalyzed reaction. So there's this difference between the activation energy for the catalyzed reaction and the activation energy for the uncatalyzed reaction right here. This is the difference in activation energy for catalyzed versus uncatalyzed. And if we can calculate that difference in activation energy, we can use the Arrhenius equation to figure out what the relative rates are by how much the catalyzed reaction speeds the reaction up. Am I speaking Greek? Is this something you did not see in general chemistry? The difference between the catalyzed and the uncatalyzed reaction and calculating the rate versus, if you know the difference in activation energy, you can calculate the difference in rates and vice versa. A for the uncatalyzed is equal to A times E to the minus EA for the uncatalyzed over RT, and K for the catalyzed reaction is equal to A times E to the minus EA for the catalyzed reaction over RT. If we want to get our relative rate, we know this one's going to be faster, right, because it's the lower activation energy. We can write K cat over K uncat, and that's equal to A times E to the minus EA over RT for the catalyzed. Exactly the same for catalyzed and uncatalyzed reactions, but it is for the halogenation, right? Because there's no orientation factor, and we've already corrected with our relative reactivities for the statistical factor. So in this case, we can really legitimately cancel A. And then E to the A over E to the B is equal to E to the A minus B. So we can write that K catalyzed over K uncatalyzed is equal to E to the, and the activation is the activation energy for the uncatalyzed reaction. Since I know this one is larger, I know this is actually going to be a negative number, so it would be productive to rearrange that and write that as, where that's always a negative number, which means the exponent will be positive, which means K cat over K uncat is going to be greater than 1. This is the difference in activation energy. So this is delta EA, and that's what I'm interested in, right? I want to know if the difference in activation energies here is similar to the difference in the product energies. Right. We call that a late transition state, and it's typical of an endothermic reaction. 1 over RT times the activation energy for the uncatalyzed reaction minus the activation energy for the catalyzed reaction, and I can multiply through by RT. RT times the ratio of the catalyzed over the uncatalyzed is equal to the difference in activation energy. So if I know by how much the catalyst increases the reaction rate, I can use that to determine the activation energy gap. Did you see all of this in Gen Chem? This derivation that says that the difference in activation energy for catalyzed versus an uncatalyzed, right, which is what we're looking at here. What we're looking at is we're looking at the formation of the secondary radical versus the formation of the primary radical. Right? That ought to be faster, forming the secondary radical. So we're going to be looking at a version of this equation that says that RT times the natural log of K for the formation of the secondary over K for the formation of the radical. The primary, right, that's going to be a positive number. The activation energy is going to be a positive number. So the difference in activation energy depends on the relative rate of formation of secondary versus primary. But that's the relative reactivities. So for bromination, we're looking at relative reactivity for primary, which is 80. And that allows us to calculate the difference in activation energy, right? So we can say that delta EA is equal to R 8.314 joules per mole Kelvin times T 298K, right? Or for bromination, actually, bromination, if you look at the numbers, the 80 to 1, it's actually at 150 degrees C, so that's not 298K, right? For chlorination, it's 298K. You have to heat the bromination reaction to get it to go. So this 150 degrees C plus 273.15 K, right? We're actually going to be using a temperature of 423.15 Kelvin, right? If we want it at that 150 degrees C. The relative reactivity is not quite 80 to 1 if you're working at a different temperature, 4.184 joules, and then we want kilocalories, so 1 kilocalorie is 1,000 joules, or sorry, 1,000 calories, and then the natural log of 80. So if you plug those numbers in and solve for the difference in activation energy, you're going to get a number that's close-ish to 2.5 kilocalories per mole. So the difference in product energies in the radical is you've gone a long way along the reaction coordinate by the time you get to that transition state. So the transition states are what we call product-like. They're late transition states. They occur late on the reaction coordinate as you go from starting material to radical. And so the difference in energy should be similar to the difference in reaction enthalpy. For chlorination, that's not true, because chlorination is an exothermic reaction, which means both of the transition states look a lot like the starting material. And if both of the transition states look a lot like the starting material, you're not going to get nearly the selectivity. The only thing that changes for chlorination is this, right? Because the relative reactivity for the secondary versus the primary for chlorination is 4, and the natural log of 4 is a lot smaller number. So the difference in activation energy for the chlorination is going to be less than 1 kilocalorie per mole. I can't remember what it is, but you'd have to actually do the calculation.
Activation energy could make things more selective.
Yeah.
How does the Hammond postulate make things more selective as well? Like, I don't understand how product like transition states.
So what the Hammond postulate says is two species, for example, a transition state and a reactive intermediate. So in this case, we're talking about this transition state where we've partially broken the bromine bond, but not completely, and this reactive intermediate, which is actually the radical. If they occur consecutively along the reaction coordinate, which they do, right? The transition state, you don't get arrangement of molecular structure. What the Hammond postulate is telling you is if the transition state is close on the reaction coordinate to the product, it's going to look like the product. And if it's close on the reaction coordinate to the reactant, it's going to look like the reactant, right? So a consequence of the Hammond postulate is that endothermic reactions, where it takes you a while along the reaction coordinate to get to the transition state, have product-like transition states, and exothermic reactions, where you get there pretty quickly, they have reactant-like transition states. Since there's only one reactant, if both of your transition states are reactant-like, they not only both look like reactant, but they look like each other too. And if they look like each other, they can't be very different in energy. The Hammond postulate says that you have to connect your points by smooth curves. You're not going to suddenly go vertical, right? Where there's a very small rearrangement of molecular structure suddenly causing a huge increase or decrease in energy. So the Hammond postulate, right? So if it's a reactant-like transition state, you can't have a very large activation energy gap between your two transition states. Whereas if it's product-like, you can have a transition energy gap that's quite large. I think if you actually do this calculation, you even come up with a transition state energy difference that's like 2.6 kilocalories per mole. That's in fact slightly larger than the difference in energy of the radicals once they're fully formed. That's somewhat unusual. It's usually a number that's slightly less. But I think if you do this calculation, you come up with a number that's large. And that may be because of the temperature difference. Because in the video I may have used 298 Kelvin, but strictly speaking I really shouldn't use 298 Kelvin because the 80-to-1 ratio that came from the table is at 150 degrees C, not 25. Does that help?
Yeah.
So the upshot, the thing you really need to kind of have as your take-home message